Hello and welcome to our lesson today. We are looking at periodic motion and behavior. So far in the unit, you've practiced working with triangles, specifically with trigonometric ratios and sine and cosine law. And of course, the trigonometric ratios that we saw with sine, cosine, and tangent, we are going to in later lessons see the functions for both sine, and we'll also slightly explore the cosine function, which is when we have different inputs for the for sine and cosine and what their outputs look like in terms of their graphs. And before we get into the graphs of those, we are going to look at periodic motion and behavior because those graphs are actually used for these kind of problems in real world applications. So we are going to first analyze when in real life might we have application problems that are repeating, and they will be having a graph or a visual representation that is a repeating cycle. So by now we have seen time and distance graphs. So we are looking at this time and distance graph here. This is a linear graph because all of these lines are linear lines, which then also means that the object is moving at a constant speed in one direction for any portion of the graph that we are looking at. So starting at point zero, at time zero, and we have time in hours and distance in kilometers. So here, after 2 hours, we have traveled to 60 kilometers. And remember, speed is distance over time. Maybe I will write that here for us. Distance over time. Or we say S is equal to D over T. And in this case, it is kilometers per hour, but of course, we can also have meters per second as one of our common units. We are working with metric, so we only really use meter and kilometer. But for example, in America, we also do have miles per hour as well. So in this portion of the time and distance graph, we have 60-kilometer distance over 2 hours of time. So then 60 divided by 2 is a 30-kilometer per hour speed. And considering a starting point, which is this point here we are moving away from the point because we are getting further away. So with time and distance graphs, yes, they do tell us the distance and time traveled, but they also tell us the direction in which we are traveling. So here, because we're moving away from this point, we say that the motion is going away. Consider, for example, a motion detector device here, and when you go this line here tells us that we are moving away from the motion detector device at a speed of 30 kilometer per hour over 2 hours. Now, this portion here, we are still at that 60 kilometer, and for 2 hours we stay at that distance. And this means no motion. That's, for example, if you are standing still, or maybe you are sitting somewhere and you're resting for 2 hours. So here you actually have a distance or a speed of 0 kilometer per hour. And that makes sense because the distance traveled is zero from 60 to 60, but this happens over 2 hours, but the 2 hours doesn't really matter for our speed because when the numerator d is zero, then it's just zero divided by anything is zero. So for our speed, it's 0 kilometers per hour. Now, in this portion, we are actually moving towards the x-axis, which is, or the this axis that we started from. So this is now the motion towards. So now we're walking again towards the motion detector. But in this case, we do travel this 60 kilometers per hour, but here over 3 hours. So now, and we can clearly see the steepness of this line is greater than the steepness of this line. So our speed in the first part is greater than our speed here. Our speed in this portion is only 20 kilometers per hour because 60 divided by 3, we get 20 kilometers per hour, and we are moving towards the motion detector. Again, we rest for another hour here. And actually, this line should be lined up with here. So ignore that minor error there. And then again, we are moving away here. And this time it's 80 kilometers over 2 hours, so it's 40 kilometer per hour, and this is our greatest speed that we see in this time and distance graph. And all of that that I just interpreted is included here. One thing also we have now, and I will define these for you in our next page, but peaks and troughs. So peak is the highest point on our graph. In this case, this is the highest point, and it tells us the maximum distance that was traveled. So when we get to this point here, which is our maximum, this is the maximum distance traveled of 80 kilometers. Now the trough, which is the lowest point, is going to be our minimum distance. So in comparison to the motion detector device, how far away do we get from it and how close do we get to it? So we at this point get 80 kilometers away, but at each of these 3 points, we are directly standing next to the motion detector device. So our distance is 0 kilometers away from the device. So that's the minimum distance there. Now, this part I also wrote for you. The steepness of each of the line segments also tells us the speed that we are traveling at. And again, that's just distance over time. And pay attention to the units that you have as well. Now, consider this other time and distance graph. This is also a linear graph as well because all of our lines are linear lines. But what do you notice about this graph? And comparing to the first graph, how is it different? Well, here we can clearly see this specific movement is repeating 6 times. So this is now a cyclic or periodic behavior because the same movement is appearing several times. So how we can interpret this one? Suppose a swimmer starts at one end of a 500-meter pool, swims to the opposite end. So here's where he's starting, goes to this end, and then swims back. So we're back at that point, and they repeat 6 laps. So this is lap 2, lap 3, lap 4, lap 5, and finally lap 6. And this graph shows the swimmer's distance from the starting end of the pool, so wherever they started from. So they go 500 meters away to the other end and then come back to where they started from. And of course, because we can interpret this as kind of like an isosceles triangle here, so we can say these two speeds are the same. So it is at each point, he is going at 500 meters, or actually, I can even interpret it as 1,000 meter over 10 minutes. And so he's traveling at 100 meter per, or swimming at 100 meter per minute. So here, now we have two different units of meter and minute. So I will respect whatever is on the graph there for my distance, for my speed, which means the swimmer has a consistent speed going towards one end and another end maintains that speed throughout. Of course, we know in real life that's maybe not as realistic. Perhaps by the 6th lap, the swimmer might be tired and the speed here might be changing, or you can even interpret at these points there might be a pause where the swimmer is flipping directions, but this is assuming that they instantly flip their direction and are swimming back. So at these points, there's no time where the swimmer has no speed and they're just consistently moving. And again, throughout these 6 laps, they maintain a consistent speed. So these are all assumptions we do have to make with these types of graphs, which is that consistency. But this is clearly an example of periodic behavior because, again, we have the same motion that's repeating several times. So now just that key vocabulary again, as I mentioned, peak and trough. So peak is the highest point on the graph and trough is the lowest point on the graph. And with application problems, we do have to interpret it in the context of the problem. So of course, in this case now, we don't have the motion detector device. We just have the starting point, which is one end of the swimming pool. And so we go 500 meters away from the that end of the pool to the other end, and that's actually the maximum distance that we can go in a 500-meter pool, and then we come back. And this is going away from the end, this is coming towards the end, and this repeats 6 times. And we can also say the swimmer was swimming for 60 minutes in total and traveled a total of 6 kilometers or 6,000 meters. Now, some more vocabulary here. A period is the interval of the independent variable, which is often time, needed for a repeating action to complete a cycle. So in this case here, we have 6 repeating cycles, and the period is 10 minutes. Each one lap back and forth takes 10 minutes, so the period will be interpreted as 10 minutes. And we can clearly see time here is my independent variable, or as we know with the x-axis or the horizontal axis, it aligns with that variable there. Now, a cycle is the series of events that are regularly repeated. So in the case of the swimmer, one cycle is going to one end of the pool and then swimming back. And it can also be a complete set of changes. For example, a seasonal change, or every year when the seasons are changing, that's one cycle throughout the year. And it's starting from one point and returning to the same point in the same way. Now, periodic functions, which as I mentioned at the beginning of this lesson, we are going to see that our sine and cosine functions are periodic functions because they will have values that are repeating at equal intervals. And this could even be a periodic function as well. And we see that this portion of it keeps repeating at equal intervals. Now, if we were graphing based on real life, as I mentioned, where the swimmer's speed might decrease at the end, and perhaps lap 6 is done in 20 minutes instead of 10 minutes, even because of that one cycle, this would no longer be a periodic function because it is not the same repeating movement at equal intervals throughout the domain of the graph. And in this case, the domain of the graph is the total 6 laps. So we do have to consider all the 6 laps. And as soon as one of them has a different interval than 10 minutes, then that's no longer a periodic function. So with periodic functions, if we extend the graph, we are able to see repeating patterns and we can actually make predictions by extrapolating. Remember, extrapolating is the process of extending your graph to determine points that aren't necessarily given to you. So if I here told you the swimmer swims a 7th lap at the same consistent speed and distance, then you would know that I can draw this over here, and I would just have this be time 70. So then it's 70 minutes of swimming, 7 laps, each one 10 minutes, and each one is 500 meters to the other side and 500 meters back. So this is that expected result that I would have based on the fact that this is a repeating function. Now, non-periodic functions are pretty much a function that has a graph that is not repeating at regular intervals, or just does not have a repeating pattern. So our quadratic function, exponential functions, these are all non-periodic functions. Now consider this graph below, and my first question to you is this a periodic function? What do you think? To determine if this is a periodic function, you're looking to see if a specific motion is being repeated over the same equal interval. So I will start here. I can see that for me to end back at this point, one option is here, but clearly I go down here again, so I can't stop here. But I could consider this whole part, and maybe I could consider this portion here. Maybe let me just extend these beyond the graph. There we go. This could be one cycle here. And now I see this happens over 5 units, and I want to see if this portion is repeating again. So clearly I see after about 3 and a bit, I'm back at that point. Yep, that part holds. I move down by 2 units and then I'm back at where I started. And this whole portion is another 5 units. So this pattern is actually repeating and it does happen over a period of 5 units. So then, yes, this is a periodic function. So how many cycles are shown on this graph? The two that are drawn for us are this cycle and this cycle. So only 2 cycles here. And what is the period? I already mentioned 5 units in this case. The reason for that is we aren't given any context for this graph, and we don't necessarily have labels for to know if this is time and what the units are. So we just say 5 units because I can count 5 here and 5 here. Now, what are the maximum and minimum values? So of course we know the maximum, maybe this is the maximum and this is the minimum. And the way we can interpret this now, consider the motion detector device is here on this line. So here is when you are moving, and let's say you're moving in front of the device this way, and then you move backwards, and at this time you're back at the motion detector device. So you're walking in front of the device and forward and back. And now let's say you go behind the device, so your direction is now in the opposite direction. So instead of going, for example, to the right, you're now going to the left. And that's what this portion is telling us. So again, consider you're going down behind the motion detector device by 2 meters, and then again, you end up back at where the motion detector device is located after another 1 unit of time. So the max, we would just say max is 4. Again, we don't have values for the units here, so 4 units, and the minimum is -2 units. And once we apply context here, then we can interpret it. You can also think of it as, for example, an elevator where it goes underground. All the levels that are above ground are positive values, and all the levels that are below are -2 or negative values. So here we start at the lobby or the ground level. We go up to 4 floors, and we come back down to the ground floor or the base floor again, and then we go down underground by 2 floors, and then we come back to the ground floor. It can also be where the elevator is automatically set up, so after each floor, it goes directly to the ground floor. Now, although with that one, I will say that one is less likely to actually be a periodic function because you are probably going at different floors. So with periodic functions, we have to be considering movements that are repeating. And so when we see the applications of these periodic functions, you'll see more of which examples actually in real life are used to, or which examples in real life use periodic functions as their graphs. Now here, what is the value when x is equal to 1? So here, x is equal to 1. We also have, and let's just say for the sake of right now, this is x and this is y. Then y is equal to 1. And also, what is the value when x is equal to 5? X is 5. We have our peak, which is 4. So y is equal to 4. So now, suppose we extend this, and not the curve, I guess, better to say the graph, in both directions by repeating the cycle. And we want to find some of these other values. So from here, I consider that I'm starting, sorry, from here, I consider that I'm starting here. So over 2 units, I go to 4. So at 10, I'm about here. And working the okay, there we go. And of course, we would extend it more this way if we had the line, but just I want to extend to the values that I have. Now from here, I do have to work backwards. So actually, let me draw this here as well to show that this is where my second cycle ends. So remember, this is one cycle. This is a second cycle. And So from the end point, now if I'm going backwards, I know that over 1 unit, I go 2 down. So I would end up here. And then again, from this side, over 2 units, I'm back at that 4. So this is my graph extended in both directions based on the values that I have so far. Now we're asked what's the value when x is equal to 10. So first, x is equal to 10, we have y is equal to 4. And then what is the value when x is equal to -4? So at -4, we have approximately y is equal to 1 again here. But now consider what is the value when x is equal to 35? So going back here, keep in mind, I can choose what the starting point and end point is. So I chose this as a cycle at the beginning because that's what was drawn for me. However, I can choose to look at it at my starting time to be, or my starting point for x to be 0. So then I'm actually just going to move these over by 2. And you can see now this is 3 complete cycles shown on this graph. And they are a repeating behavior. And just to keep it in order, this is 1 cycle, 2 cycle, and then we will have the 3rd cycle. And so now I can have these cycles of 5 with a period of 5, and I can actually interpret when each of these values for future values are with respect to uh, their divisibility by 5. So any value that's going to be a multiple of 5, as I can see 0, 5, 10, or -5, at those times, the y value is equal to 4. Same with here as well. So then, when x is equal to 35, following this pattern, I will have this shape or this point, which is my maximum. So that's exactly what I've written for you here. So suppose we consider the cycle from x is equal to 0 to x is equal to 5. So when x is equal to 35, one cycle has just ended, and at the end of that cycle, the value is 4. So then, for any integer n, we can conclude that when x is equal to 5n, the value is 4. This is also to say any multiple of 5. And we do say integer because we also go in the negative direction as well. As we saw here, -5 has a value of 4. And if I continue, -10 will have a value of 4, and so on. Next, what is the value when x is equal to 72? So again, we have to consider when we're thinking of cycles of 5, where is 72 with respect to that cycle? So again, thinking of multiples of 5, at x is equal to 70, which is a multiple of 5, one cycle has just ended, which means that we are here and this would be 70. So then, or perhaps let me show you here, 70. So then at 72, that's 2 units after, we expect to be down here at -2. And that's exactly what the value will be at x is equal to 72. And just to generalize it as well, any multiple of, oh, this should be +2, sorry. Any multiple of 5, and then if you move 2 forward, the value is going to be -2. So think of all the values of 5 as, or multiples of 5 as we just said, are these peaks. Then if you add 2 to them, then you will end up at this trough here, which has a value of -2. And that's exactly how we extend periodic graphs to be able to extrapolate future values or values that are not shown on our graphs. Now, another application problem, and this is our last example for this lesson. A factory that makes rubber hoses uses a chopping machine. Each hose is cut to be 5 meters in length. The graph shows the process of this chopping machine. So let's interpret this graph here. We start at time 0 here, and each time the graph is going down, and we are we're chopping the hose at that time. And we can see this behavior is repeating every 2 seconds in time. And that's what we have here. The cutting blade cuts a new section of the hose every 2 seconds. And we see the period of 2 seconds as written for us here. Now, this maximum that we see here tells us that the height of the blade, so consider the blade goes up and then comes down. So the height is always 2 centimeters or less. So at the time it goes to the top position for the cutting blade, this is 2 centimeters, and then it goes back down to cut the hose. So the blade cannot be higher than 2 centimeters, and when the height is 0 centimeters, the blade is hitting the cutting surface. So, of course, here we can interpret the maximum and the minimum as 2 centimeters and 3 centimeters, or sorry, 2 centimeters and 0 centimeters. And the interpretation in the context of the problem is at 2 centimeters, the blade is at its top position, and at 0 centimeters, it's down and cutting the hose. Now, we also see these flat sections here, and um, these tell us that there's no movement happening at that time. So consider a machine, and at this time, the machine is processing the hose and moving the next portion of the hose over so that we can cut another 5 centimeters. And at that time, the blade stays up for the hose to move over, and then it goes back down again. And that's precisely what we're seeing here. And these lines the diagonal lines, we can also determine the speed of the chopping machine as well. So we can see approximately in these portions. So for example, from 5.5 here to 5.75, it takes 0.25 seconds for the machine to go down. Or again, from 5.75 to time 6, it takes 0.25 seconds for the machine to go up. So each up and down motion is 0.25 seconds. And we can actually determine the speed because we know that every time it goes up and down, it travels 2 centimeters, as we just said from the maximum and minimum, and it does this in 0.25 seconds. So this is a speed of 8 centimeter per second. So pretty fast machine. And that is the interpretation of this graph with relation to the application problem. And this is actually one really common example of periodic motion, which is machinery that are used in factories that have the same repeating motion over and over at a consistent rate. And of course, there will be in real world problems, times where the machine has a fault, something happens where the machine stops for a short period of time. But as a general rule, without those faults, we can assume a periodic motion and we can consider at time 2 hours where exactly is the movement of the blade depending on this periodic motion here. So that was it for our introduction to periodic motions and behaviors. So I do suggest that you try to think of other real world applications where periodic motion may be useful and can be used to graph certain repeating behavior. And please check Google Classroom and complete these practice set questions below for extra practice. And as always, don't hesitate to reach out if you have any questions, and I'll see you all in our next class.